So in this video, we'll be reviewing for the final exam. This is the practice final that you can find on Blackboard. Okay, so looking at question 1, it says given that the integral over the interval of -1 to 1 of e to the negative x squared dx is equal to k, find the same integrand but over the interval of 0 to 1. So if we know the characteristics of e to the x squared, and we can take a sneak peek and see what's going on in the calculator. But if you don't know that it's an even function, you can pick it up, like I said, from the calculator. I have the trace function enabled here. Let me get rid of that. Oop, I don't think I can, or at least not easily. So I'll do that later. But anyway, it's an even function because all powers, I mean, there's different ways of verifying it, but all powers in the expression are even, or if you replace x with a negative x and simplify, you get the same function that you started with. All right? Because this is even, we're looking at something that's symmetric over the y-axis. Because it's symmetric over the y-axis, we're going to have equal parts of area on the left side of the axis as we would have on the right side of the axis. Right? So that makes things pretty simple, because if we know that the whole thing going from -1 to 1, I'll just kind of bring it in so it's a little easier to see. I'll even really bring it in. But the whole thing is equal to k over that interval, and all parts of this graph are above the x-axis, so there's no part that's going to be canceled out in any way. Then each part would have to be half of k. So this would be half of k, and then this would have to be half of k. I'll use the same writing style. Anyway, they said going from 0 to 1, that would be the red. So half k, so k over 2. All right. Number 2, let R be a region in the first quadrant enclosed by the curves given. And the y-axis, find the area of the enclosed region. All right, so it's just a question of which way do you want to go with this. All right, does it make sense to do this with respect to x or with respect to y? So it looks like I have a region that's entirely bounded between two functions if I look at rectangles that have a thickness along the x-axis. All right, I can get from the beginning to the end of that interval with that information. All right, but two things I want to check. One is just kind of a mental check, and that is that it does have an x and y intercept of 0. It goes through the origin, that line. All right, so we're good to go there. All right, and the other thing that I want to check is that the two graphs intersect where I think they intersect. All right, so I'm going to put them in. 2 minus x, 2 plus x. I think they intersect at 1, 3, but I could be a decimal situation. All right, so take a look at the picture. Calc, second trace, 5, enter is what you want to do. All right, but let's see if I can remember how to do it on this thing. Close it here. Second trace 5, enter. It's going to be 1, 3, but I can also just look at the table. All right, so 1, 3, 1, 3 for both the graphs, so we're in good shape there. All right, so what I would want to do, go back to black, again black. So over the interval of 0 to 2, I'm I'm going to find the difference between the parabola, the dominant function, and the non-dominant function with respect to x. And I could do that all in the calculator because I stored this one in as y1 and this one is as y2. So math 9. I'm sorry, math 9. Almost corrected myself to the wrong thing. Alpha trace y1 minus alpha trace y2, close it up, dx, going from 0 to 2. All right, and we're going to have, that's negative 2/3, which is not the right answer. Okay. Oh, 0 to 2. Why did I say 0 to 2? Nobody knows. 0 to 1. Yeah, that would have actually included some area that we didn't want. That would have been a reversal of it. That would have had all this stuff in there. That's no good. Let's do that again, shall we? Using a technique I like to call the right way. Sorry, that was Chewbacca in the background. So that is more like it. You can math bracket if you don't recognize the decimal, 13/6. All right, number 3. Oops. The area between y equals x squared and y equals 4x minus x squared is rotated about the y-axis. Find its volume. So let's take a look at the picture. X squared, 4x minus x squared. Take a look. Just so happens that a nice window already set up, but this is what you'd most likely be presented with, something along these lines. Then you'd have to bring it in and you say, okay, I got this little rose petal kind of thing going on here. But that's getting revolved around the y-axis. So I'm just going to do a rough sketch of that. Right, so I'm going to have this one, and I'm going to have this one. All right, so this is my y equals 4x minus x squared, and this is my y equals x squared. And we're swinging this around the y-axis, so it's just a question of what technique you want to use. All right, so it's really dealer's choice. If you don't really have a sense going in, it's not going to be the disk method. So it's a question of, are you going to do washers or are you going to do cylindrical shells? Ideally, you do cylindrical shells because it's easier. So we try to make that work. All right, so here is an arbitrary rectangle that is a little out of whack. So I'm going to do that again. Oh, that's a little on the thick side. Too much. Let's bring it down to like 1.7, I think. Yeah, a little bit better. All right. So distance from the axis of revolution, we call that P. H is the height of the arbitrary rectangle, and D, X in this case, because the thickness is along the x-axis. All right, so 2 pi over the interval. Well, it's going to span from here to here, so I need to know where they intersect. So it's going to be from 0 to something. All right, now my guess is it's 2 or 3. It looks like 4 if I do a proper zoom here, but I can also just go into the table, take a look at 2, 4. So on the x-axis, so for cylindrical shells, I would want 2. If I were doing a washer method, I would want 4. All right, the P is the distance from the axis of revolution to the center of the arbitrary rectangle. which is the distance from the y-axis to some arbitrary point in space, which we're going to call x. H is the difference between these two y values. So we'll call this y1, and this one I'll call y2. So H. So the H is just going to be that vertical distance of the rectangle, which is going to be the red curve minus the black curve. So 4x minus x squared minus another x squared. So we could say 4x minus 2x squared. All right, so this is what we're looking to integrate. So math 9, pop in my 2 pi first to x 4x minus 2x squared, close it up, dx over the interval of 0 to 2, and you get about 16.8. There's a volume, so units cubed. All right, so now if we wanted to do that, so that's the shells method, so cylindrical shells. All right, so let's say we wanted to do that with the washer method. I'm going to steal my diagram here. A lot of it will remain the same, but some of it will change, particularly the orientation of the rectangle. So we got to kind of start there. Got a little too ambitious. Okay, so we don't need the pH and stuff like that. All right, now we do know that this intersects at 4 in terms of y. All right, so if I'm looking at an arbitrary rectangle with respect to the y-axis, I'd have to find the difference between oops, I put my my red one in the wrong place. The black one and the red one. Oh, if I can get it to look the way I want it to. There we go. All right, so each of these are x values. Corresponding with a dy. So I need a pi r squared for the dy, and from that I'm going to subtract a pi r squared for the inner figure as they get spun around the axis. All right, over the interval in both cases it appears to be 0 to 4, so we have no changing of dominance in terms of the function. So 0 to 4 in both cases, so we're good there. All right. So I just need to solve for x in both cases. All right, so this one would be x is equal to the square root of y. And I guess I don't need those subscripts anymore either, so let me get rid of those. Now the other one, that's a little bit of a different story, right? Because if I want to solve for x, you could think about doing it a couple of different ways. One way might be to try to factor out an x. All right, I'll show you really quickly. It doesn't really get you very far. So I pull out an x, you get a 4 minus x, and you're like, all right, I'll solve for x. And you're going to get yeah, you'll solve for x, but it'll be in terms of x, so that doesn't really do you any good. All right, so we could try completing the square. So take the b value, cut it in half, and square it. So I use b squared over 4a. So the b is 4 squared. Well, the b is 4. Squared is 4 squared. Over 4 times negative 1. Sorry, my hand's hitting the calculator here. All right, so we're looking at negative 4. All right, because 16 over negative 4. So that would be my number to be popped into the gap here. Just got to go on the other side. So if you're already thinking, well, I like that cylindrical shell method better, I hear what you're saying. All right, so this, I need to factor out a negative. So 4 minus 4x plus x squared. So that's going to be negative 2 minus x, the quantity squared, is equal to y minus 4. And I'm going to give myself some more room, move this around a little bit. All right, negate both sides. So 4 minus y is equal to 2 minus x squared. Take the root of both sides. It's just a question of which, you're concerned with. Yeah, I mean, are you looking for the positive or the negative? You see, I kind of glossed over that up here, but it's just kind of habit at this point where if we're looking at a first quadrant value or expression, its odds are it's a positive, but that doesn't mean I shouldn't check, so that's what I'll do. All right, so let me bring up my Desmos calculator. Bringing up my Desmos calculator. Just do it this way. Got to get kind of cute with this. Oop. There. Try to do it as a floating kind of thing here. So I'm looking at y equals x squared originally. All right. I drew it in black, so I'll make it black on my screen here. Right. Now, x equals the square root of y. Now again, I only care about the part of this that's in the first quadrant. So x is equal to the square root of y. All right. So we just verify that it's giving me the appropriate piece. Now, if you want to do it more intuitively, it's fine. It's just, you have the technology, so why not at least use it to verify your work? It's just a thought. I mean, because most people are comfortable with the idea that, all right, positive in terms of x means above the x-axis, positive in terms of y means to the right of the y-axis. So, it's like, it's up to you how you want to do it. I just figured I'd present this as an option. So then the other one, which is a little less user-friendly, we had y equals 4x minus x squared. All right. And so now I didn't finish solving this, but it would be, if I solve for x, it would be x is equal to 2 minus the square root of 4 minus y. So let me type that in. X is equal, I'll write it down in a minute, but 2 minus the square root of 4 minus y. All right. So looking at that and comparing it with the piece that we had before, it looks like that's what we want. All right. Now, we put it all together, like everything seems to go. But let's get rid of the ones that we don't want. And it seems like that's working out the way we do want it. All right. That's the graph. I mean, my hand-drawn graph isn't picture perfect, but it gets the job done. All right. So we're in good shape with the positive roots. All right, so again, like I said, this should be x is equal to 2 minus the square root of 4 minus y. All right, so if I want to evaluate this, and I do, it would be, just got to keep track of which is which. All right, so it's the square root of y squared dy minus pi, still over the interval of 0 to 4, 2 minus the square root of 4 minus y as a quantity squared dy. So all that has to go in. Some of you could do easily enough by hand. So this is really pi over the interval of 0 to 4 y dy minus, everything else is going to stay put, but I can at least kind of save myself a little bit of time, or a little bit of, maybe not time, but typing. 1/2 y squared over the interval of 0 to 4. That whole thing multiplied by pi. 4 squared is 16, divided by 2 is 8, so 8 pi. And then minus that whole decimal, or I'm jumping the gun here, making the assumption that this is going to be a decimal. But, we did it with shells, so that's a logical assumption. But now I'm just going to type in 8 pi minus pi, math 9, parens 2 minus the square root of 4 minus, you use whatever you want, I'm going to use x. Close it up, square it, x over the interval of 0 to 4. Quick double check. 16.756. 16.755. Either way, it's going to round to the same thing. So about 16.8. So in number 4, we're looking at something that has a pair of factors that are being multiplied, has a product relationship. So it seems to fit the mold of integration by parts. And with integration by parts, we want to define a u and a dv, where the u is something that you could find the derivative of. And in doing so, you'll make the expression simpler, right? Or make the process simpler. Right? The dv is something that you could find the antiderivative of while not making anything more complicated. It doesn't have to make it simpler, but it shouldn't make things more complicated. All right, so du, ln of 2x, you can look at it a couple different ways. It's 1 over 2x times 2, or you can kind of sort of split it off and say this is ln of 2 plus ln of x. This is constant, so that goes to 0. ln of x is 1 over x, so 1 over x dx. Now v is going to be 1/4 x to the 4th. All right, it was originally a power relation. It's still a power relation. Didn't make things more complicated. All right, so uv minus the integral of v du. So u is ln of 2x. V is 1/4 x to the 4th. So put them together, unless you want to use the expanded form. But if you put them together, we're looking at 1/4 x to the 4th ln of 2x minus the integral of v du. So put these two together, and we're looking at 1/4 x to the 3rd dx. Pretty easy to integrate that. All right, so 1 over 16 x to the 4th plus c, don't forget the minus, and we have all this other stuff coming along for the ride. All All right, so that's number 4. Looking at number 5. This looks like partial fractions. All right, so unless you want to, well, one, take your chances that this is also going to be a multiple choice question on the final, not guaranteed. And also, the other part of that is waste your time trying to find the derivative of each one of these choices to see which one matches up with that integrand. I'd say definitely want to review partial fraction decomposition techniques. All right. And if anybody's planning on going on to any form of differential equations in the upcoming semesters, you're going to need to know this. All right. Comes up in Calc 3 also, so you definitely want to know. All right, so we have a power of 2 binomial and we have a power of 1 binomial. All right, both linear. So I'm going to rewrite. We'll start off with the power of 2, 1. All right. So the way we handle that is we start off with that binomial as a denominator as if it's not raised to a power at all. Its numerator, because the denominator is linear, the numerator should be constant. It's always 1 degree less than whatever the denominator is, all right, or at least the inner function of the denominator. So this we're going to call a sub 1 plus. Now we have our x plus 3 squared, all right? So if this were x plus 3 to the 18th power, you'd have an x plus 3 squared, x plus 3 cubed, x plus 3 to the 4th, all the way up to x plus 3 to the 18th. So a sub 2, and then I'll address my 3 minus x. Now we could factor out a -1 and make that x minus 3. I don't know that that advances the plot too much, so I'm just going to leave it as is until I have reason to change. All right. So what we're going to do is multiply everything by our common denominator. All right. So that's going to wipe out all the denominator, all the components of the denominator on the left. We're going to be left with, we still have the a sub 1. We'll be left with an x plus 3 and a 3 minus x. A sub 2 will be left with a 3 minus x. And a sub 3 will be left with an x plus 3 squared. All right, so we can distribute now. Now I have cause to rewrite this. I'm going to write this as negative parentheses x minus 3. The reason why is because I can now very easily distribute those two. So I'm going to say negative a1 times x squared minus 9 plus 3a sub 2 minus x a sub 2. The last one, we're just kind of stuck with it. X squared plus 6x plus 9. A little bit more distributing. Negative a sub 1x squared plus 9a sub 1 plus 3a sub 2 minus x a sub 2 plus a sub 3x squared plus a sub 3, or well, 6x a sub 3 plus, shift it over. Actually, I'll shrink it down a little bit. Just a little bit. So then 9a sub 3. All right. Now, the x squared terms, let's see, there appear to be 2 of them, barring any algebraic mistakes. These 2 terms are going to amount to nothing because there is no x squared term on the left-hand side. the x terms, also going to amount to nothing. So negative a sub 2 plus 6a sub 3. But the 9a sub 1 plus 3a sub 2 plus 9a sub 3 will all add to equal 3 somehow. All right, now all of our coefficients are multiples of 3, so that'll help a little bit. 3a sub 1 plus a sub 2 plus 3a sub 3 is equal to 1. All right. Now, making a substitution is going to be helpful in some capacity. And it's just a question of which way we're going to go. So what I'm going to do here is I'm going to try to get this big beefy equation down to just one variable. All right. So I can take this and solve it for a sub 3 or a sub 1, it doesn't matter, but it seems to be a little easier to solve for a sub 3. But now I have equality between a sub 3 and a sub 1, so I definitely can go either way with that. All right. For this one, I can say that 6a sub 3 is equal to a sub 2. All right, so I have an easy way of swapping out an a sub 2 by replacing it with a 6a sub 3. I already have an a sub 3 there, 3a sub 3. So it kind of leads me to think that my best bet is probably to replace the a sub 1 with an a sub 3. All right, so 3, 6, 12. A sub 3 is equal to 1, which means a sub 3 is equal to 1/12. Which means a sub 1 is also equal to 1/12. A sub 2 is 6 times a sub 3. All right, so 6 times 1/12, 6/12, or 1/2. All right, so all of that to get us to something that's more integrable. All right, so 1/12 over x plus 3 plus 1/2 over x plus 3 squared plus 1/12 over 3 minus x dx. So I took a second and I typed it in the integrand into the handy dandy Desmos here, just to give you a quick visual that what we have is equivalent to what we started with. Important realization. Now, the first and the last one, they're pretty easy to identify in terms of the integrals. All right, so the first one is going to be, 1/12 ln x plus 3, sorry. This last one here, the middle one we'll deal with in a sec, but this last one, it would be 1/12. We could say ln 3 minus x. Now if we go to check this, when we check it, we would say 1 over 3 minus x times the derivative on the inside, which would be a -1. We have to correct for that, so we're going to negate this one. All right. So we have a 1/12 ln x plus 3 and a -1/12 ln 3 minus x. All right, for whatever that's worth. I could actually group those together. Write it as 1/12 ln x plus 3 minus 1/12 ln 3 minus x, and then add to that, I'm going to rewrite this one as x plus 3, well I forgot the 1/2, to the -2 dx. All right, for this one, I'm going to increase the exponent by 1, divide by the new exponent. All right, the inner function here has a derivative equal to 1, so it's not going to impact anything. So increase the exponent by 1, divide by the new exponent. we're going to have negative 1/2 x plus 3 to the negative first plus c. Everything else will stay put. All right, so now I'm just going to take a look at my choices and see what we're up against here. All right, so let's see here. This one only has the ln 3 minus x. This one, I don't even know. This doesn't look remotely like anything that we have here. So we can start off by eliminating the choices that don't make any sense. The coefficients on 4 are otherworldly. And A, I don't see any ln's. And B is the only one that looks appropriate. Let's see, we got the negative 1. Well, if we bring the x plus 3 to the negative first down to the bottom, that would fit. And the quotient rule for logarithms tells me that if I, so I'll just kind of talk you through it. If I factor out the 1/12, I'd have an ln of x plus 3 minus ln of 3 minus x. The quotient rule tells me that I can make that subtraction into a quotient. So this one is the fit, and therefore the winner. And so that was a little bit of a ride, obviously, but you know, it's definitely, I call it an indicator question. You know, it's a good question. You understand the concept if you can handle a question like this. All right. Number 6 is a trig substitution problem. Now this is in the form of, you see the numerical value comes first, so this looks like an arc sine situation. So I'm going to draw a triangle. So the a value is going to be 9, the u value is going to be x. All right, I want to get a sine ratio out of this, opposite over hypotenuse. We're going to have the 81. Come on, lock in. It's not locking in. All right, let me zoom in. 81 minus x squared. All right, so sine of theta is equal to x over 9. All right. Now, just to forewarn you, I know there's shortcuts for this stuff, but you got to understand on the test, on the exam, I could ask you, and this is my way of saying that I will ask you, to use specifically the trig substitution technique. All right, so you got to show me the work. All right, so kind of giving a little spoiler to how the question is going to be phrased on the test. All right, I'm going to ask you to show the work using this method, this very method. All right, so if you show something that involves some kind of shortcut, it's not going to get you any credit. All right. The next ratio that we get is the radical to the constant. So cosine of theta is the radical. I'm not going to try to draw that radical again. Over the constant. So we're going to have x is equal to 9 sine theta. Derivative dx is equal to 9 cosine theta d theta. And then 9 cosine theta is equal to the radical. All right, and so I can replace the x, get a highlighter here, this x with this. I can replace the radical with this, and I can replace the dx with the 9 cosine theta d theta. All right, so 9 sine theta, because that x is squared, and then we'll have a 9 cosine theta. Simplify, nice cancellations here. D theta over 81 sine squared theta So we're looking at 1 over 81 cosecant squared theta d theta. The antiderivative of negative cosecant squared is cotangent, right? Because derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. So the antiderivative of cosecant squared would be negative cotangent. So negative 1 over 81 cotangent theta plus c. Now cotangent is adjacent over opposite. So negative 1 over 81, the adjacent side is the radical 81 plus x squared. The opposite side is x, and then we'll have our plus c. So the one that looks like that is the one that we want. All right, so it looks like choice B. So in number 7, it says find the arc length of y squared minus 3x equals 0 from 0 to 3. So I'm going to pop that in real quick. All right, so y squared, let me just get a better zoom here. Minus 3x equals 0. And I only care about from 0 to 3. From x equals 0 to x equals 3. All right. So what I want to do is first take note of the arc length formula. All right. So the integral over the interval of, well, a to b, c to d, depending on your approach, 1 plus f prime of x squared dx, or same idea, just with respect to y. All right. So since the x values are given as the beginning and the end, it kind of behooves us to focus on this one. Oh, that would have been nice. What can you do? All right. So what I'm going to do is I'm going to solve this for x. All right. So I'm going to have y squared minus 3x. I'm sorry, I'm solving for y in terms of x. So y squared equals 3x. Y is going to be equal to the square root of 3x plus or minus. All right. So if I say positive, that's going to give me one piece. If I say negative, that'll give me the other piece. All right. So fortunately, we have symmetry here, so we can rely on that. So what I'll do is I'll work with just one function. So y equals 3x to the 1/2. That's this one. So y prime 1/2 3x to the negative 1/2 times 3. All right. Now we do need to square that. So y prime, f prime, whatever you want to call it, squared. All right. So that's going to give us, I mean, you might want to clean it up first. It's really up to you. Maybe I'll do that first. So this is 3/2 times 1 over the square root of 3x. So when you square it, it's going to give you a 9/4 times 1 over 3x. Instead of having the radical there, it's just a clean 3x. All right. So 3 goes into 9 3 times. So 3 over 4x. Just makes it a little bit neater. All right. So I'm going to integrate over the interval of 0 to 3. The radical 1 plus, I've already squared it, so 3 over 4x dx. So integrate 0 3, radical. I get paranoid about parentheses with these things. These computers. 3 over 4x. dx. So I got the 4.43 blah blah blah. However, they wanted the arc length of this graph, which is a sideways parabola, over the interval of 0 to 3. They didn't specify that it was just the top half. All right, so it's kind of a trick question. What we just figured out was this one piece, and it's kind of steering you to that choice. However, if I double this, I get 8.874. So choice A is the appropriate one because we also have to account for this piece, because that's still part of the graph over the correct interval. All right, because they never specified that the original relation was that of a function. All right, so we've got to be very careful about things like that. So we double this and we get approximately 8.874 units. All right, number 8. Fill in the blanks to make the true sentence. It's either going to converge or diverge, and it's going to do that by something, one of the tests. Now, I see both parts are raised to the nth power. So that makes me think that we're looking at the root test. So what I'll do is I'll raise both to the 1 over n power, or take the nth root of the top and bottom. The limit as n approaches infinity of that relation or that expression should be less than 1. All right, same kind of structure as the, or at least this part of it, as the ratio test. So we have 2 plus n over n which amounts to, well, you just got to be careful. The powers are the same. So it's the ratio of the leading coefficients. So we get the coefficient here and here. 1 over 1 is 1. So the limit as n approaches infinity of 1 is 1. So the question is 1 less than 1? And the answer is no. So this diverges by the root test. All right, so number 9, we need a Taylor series around x equals 0 for this integral. So we'll start off with the cosine of 2x part of it. So we'll just call that f of x. F prime of x is going to be negative 2 sine 2x. F double prime is going to be negative 4 cosine 2x. F triple prime is going to be positive 8 sine 2x. And then fourth derivative, 16 cosine 2x. Now, when we evaluate it from when x is equal to 0, we know that all the signs are going to get wiped out. All right. So f of 0 is going to be equal to just a 1. F double prime of 0 is going to be equal to a negative 4. F triple prime of 0 is going to be equal to a positive 16. All right, so it's alternating, but we have the power of 2 thing going on here. Or I'm sorry, power of 4 thing going on here. So we could say 4 to the 0th, 4 to the 1st, 4 to the 2nd, and so on. Or we could say 2 to the 0th. So you kind of make a case either way because 4 is a multiple of 2. So this is really 2 to the 0th or 4 to the 0th. This is either 2 to the 2nd or 4 to the 1st. 2 to the 4th. Oh, sorry. I put a 3 here for some reason. 2 to the 4th or 4 to the 2nd. All right. So when you're building your Taylor series, you could actually go either way with it. All right. So I'm going to write it out. I'm going to write the first few terms of it. Cosine 2x. So normally it would be 1. So positive 1, then minus, then you'd have your second term, which would be your 1 over 2 factorial x squared, and then, and then on and on and on from there. Right? But now we have to account for that power. If you want, you could put the ordinary Taylor series here. You could say that it would be cosine of x would be equal to 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, and so on, just knowing that our numerators are about to change. Denominators are going to remain the same, so you can kind of steal some of that. Still centered around 0, so that makes it a little nicer. All right. The benefit of going with powers of 2 as opposed to powers of 4 is that it's going to correspond with whatever rule you develop for the denominator. All right. So 2 to the 0th give you the 1, 2 to the 2nd, 2 to the 4th, that's our 4th derivative. Then obviously 2 to the 6th, 2 to the 8th, 2 to the whatever. Right? So we have the alternating aspect of it. We have everything else going on too. All right? So then building from there, we would say 1 minus cosine 2x. It would be 1 minus all of the stuff that we just came up with. Notice how I'm not bothering with a general rule yet, because I feel like that's, you're kind of spinning your wheels doing that. We'll come up with a general rule just to say, okay, now that I have that, well, I'm going to manipulate the whole series again anyway and make that rule irrelevant. All right? Now what's going to happen here is I'm going to distribute. All my signs are going to get reversed. All right? So the 1 minus 1 is going to cancel away, which is great. Everything else is going to stay put. But the signs are going to be reversed. I like to have 3 or 4 terms of a series. So I'm going to include the 8th power. Because we have 3, I'd like to get a 4th one in there. Plus, minus, plus, so then minus. All right. So the next up is going to be everything divided by 2. That's actually going to be a pretty nice adjustment. So I'm going to take everything that we just came up with, each term, and divide it by 2. Which is really just going to reduce the power of 2 in the numerator by a factor of 1. All right, so instead of 2 to the 2nd, it's 2 to the 1st. Instead of 2 to the 3rd, or 2 to the 4th, it's 2 to the 3rd, 2 to the 5th, 2 to the 7th. So instead of it being an even relationship now, it's becoming an odd relationship. So then the only thing that's left to do is the actual point of the question, finding the antiderivative. All right, so the antiderivative of 1 minus cosine 2x over 2 dx. Increase the exponent by 1, divide by the new exponent. All right, so I'm going to copy paste again. So increasing the exponent by 1 makes a 2 into a 3. Divide by the new exponent. Now that 3 times 2 factorial is the same as 3 factorial. Increase the exponent by 1. Divide by the new exponent, which makes a 5 factorial. Increase the exponent by 1. Divide by the new exponent, which makes a 7 factorial. Increase the exponent by 1. Divide by the new exponent makes a 9 factorial. So we'll start generalizing now. And in doing so, I prefer to start off with 0 wherever possible, so that's what I'm going to do. All right, so we need to have 2 being raised to an odd number power. All right, so double n and add 1 to it. So 2n plus 1. If I plug in a 0, I get a 1. If I plug in a 1, I get a 3, and so on. All right, the signs need to alternate, starting with an even power giving us a positive number. So negative 1 to the nth will get the job done there. All right, this whole thing is going to be over an odd number, but the relationship between this odd number on the bottom and the odd number on the top is it's always offset by 2 units. So whatever we came up with on the top, we can use that to help us get the bottom, just 2 more than that, so 2n plus 3 factorial, and that is going to have the same value as the exponent for x. So all that plus c is our antiderivative. So then number 10 is asking us to use the Maclaurin to prove that the derivative of this is that, So it's the same general idea, except we're using a different function and we're doing something else with it. So it's the same but different. So we'll start off with f of x, e to the ax plus b, f prime, a e to the ax plus b, double prime, a squared e to the ax plus b. So it seems like the level of the derivative is going to correspond to the power of the expression. So that's good to know. And by expression, I mean a. Right? So we'll hang on to that for a second, but if I'm going to make the assumption that the nth derivative is going to be a to the nth e to the x, ax plus b, it's a reasonable assumption. So now we're using Maclaurin, so that's where it's centered around 0. So let's find f of 0. All right. So if I plug in a 0 for x, I'm getting e to the b. All right. F prime of 0 will be a e to the b. F double prime of 0, a squared e to the b. Triple, quadruple, whatever, it's going to be based off whatever the level of the derivative is, a to the nth e to the b. All right, so we're in good shape there. So now we can do this a couple of different ways like we did in the previous one. we could start off with just our knowledge of e to the x, which is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on. Poor quality 3, let me fix that. So now I'm going to write e to the ax plus b using this information here. So same general structure, except now my numerators are going to be different. So e to the b plus my first derivative was a e to the b. Still have the x there. Plus, instead of 1 over 2 factorial, it's going to be a squared e to the b over 2 factorial. Plus, reasonable assumption would be a cubed e to the b over 3 factorial. Let me just tuck in the x squared that I forgot. And then x cubed. And then we can go all the way around. We can go to the nth term if we want. It's really not necessary because we still have to find a derivative, but we could. I'm going to. Because it's going to be a to the nth e to the b over n factorial x to the nth. All right. There's stuff in there. All right, so now what I want to do, because now we have an expression that represents f of x, I want to find the derivative of that. All right, so the constant's going to go to 0. So e to the b goes to e to the b. I'm sorry, e to the b goes to e to the b. E to the b is constant, it goes to 0. A e to the bx goes to a e to the b. Plus, now this is where things get a little bit more interesting. So let me copy, paste. So this 2, decrease the exponent by 1, multiply the exponent by the coefficient. So we're going to get a 2 here, but we're going to lose the exponent. All right. We're going to get, this is going to get reduced by 1. That power becomes the coefficient, or gets multiplied by the coefficient. And we lose a power of 1 in the exponent. And then in the general rule, just move things over, put a little plus sign in there. The n gets multiplied, and we're reducing the power by 1. All right. So in the process of carrying out this term by term, we're actually coming up with a general rule as we go. So there's, some people like to do it one way or the other. Some people like to do it both ways. It really is up to you. All right. Now, 2 factorial is the same as 2 times 1 factorial. I mean, you might say 2 times 1, but that won't prove my point. 3 factorial is the same as 3 times 2 factorial. N factorial is the same as n times n minus 1 factorial. The reason I'm writing it like this is because in each case we can cancel out part of the numerator. All right. So these are gone too. All right. We've also developed consistency between our factorial and our exponent, which is a good thing. All right, so when we're developing our expression, we can actually just kind of leave it at that. Right? Now, that being said, our goal here is not to come up with, if you reread the question, it's not to come up with a series representative of the derivative. It's actually to prove that f prime of x is a times e to the ax plus b. All right, so I'm going to rewrite this, make it look a little nicer. I keep just wanting to eliminate x's for some reason. Don't know why. There it is. All right, so this is what we have now. We have a common factor of e to the b that could be pulled out, but we also have an extra factor of a. If we compare that to what we have over here, you really see that we're only one minor adjustment away from having what we need. All right, so I'm going to pull out an a. That's going to leave me e to the b plus, instead of a squared e to the bx, I'm going to write it as a e to the bx plus, instead of a cubed, it's going to be a squared e to the b over 2 factorial x squared plus dot, dot, dot. You know what? I could even go a third term if I want, because I could just follow that trend. A to the third e to the b over 3 factorial x cubed, and then I can go to my general term. But you can see that the trend that we have here is exactly the same as what we came up with for e to the ax plus b. The only difference is we have a factor of a associated with it, and once we make that recognition, we have our proof.